Hello, welcome to the course on Introduction to Research, in particular the lecture on data analysis. In the previous lectures, you have learnt what is meant by research. We have tried to give you an overview of research, and of course, we have also gone through a lecture on literature review. In this lecture, we will specifically look at what is data analysis, the types of analysis, and the different types of data that one encounters in data analysis, and of course, a systematic procedure. We will end the lecture with two hands-on examples in a language or in a software platform called R, which is an open source free software for statistical data analysis. Now, before we proceed further, let me tell you that data analysis is an integral part of any research work. In every type of research that one carries out, invariably one collects some data or the other. Even if it is theoretical research, at some point in time, there is a bit of experimental work involved to corroborate the theory that has been developed. By and large, if you look at today, the scenario is about data analytics. A lot of data is being generated, not just in engineering arena, but everywhere, and therefore, there is a need to understand how to analyze data in a systematic manner. There are many software packages that can carry out analysis of different types of data, and one should remember that analyzing data is not just about throwing data into the software packages and then reporting some of the fancy graphs that are generated and some nice results that you get on your computer screen. That is not data analysis, it is just a very tiny part of that exercise. As much as we are analyzing data, there is a theory to it, and of course, we are not going to go over the theory of data analysis, but the procedure that one needs to follow to get meaningful results. First of all, we need to ask, what is data analysis? Analysis of data is about extracting useful, relevant and meaningful information from observations. As I said, we collect data in different spheres, in different forms, whether it is econometrics, whether it is engineering or medicine or any other field. We have different types of data collected, and the purpose of collecting data is basically to know something about the process. But of course, that is not the only purpose. As I have listed here, there are several purposes to data analysis. It could be commonly a common purpose is, for example, parameter estimation, where we are inferring certain unknowns, and when I say parameters here, it is not just model parameters. These parameters could also refer to statistical properties that we are commonly interested in, such as averages, that is mean, variability, variance or standard deviation, median and so on. So, the term parameter here should be taken in a very generic manner. Essentially, it is an unknown that we are trying to estimate from data. Obviously, that is one of the common exercises in data analysis. Then of course, we have the ubiquitous model development. Many of us collect data to develop models between two or more variables. And why do we develop models? Largely for predicting the variable of interest. A technical term for prediction is also forecasting in econometrics and social sciences. Is a very common term, and that is a huge field in itself. And then we have feature extraction. So, if you take for example, biomedical data such as ECG or EEG data. In ECG data, whether we have seen it or not, but ECG is something that we all get to see, whether it is a part of our research work or not, it is related to our human health. And if you recall, ECG is a train, it is a train of pulses which has regular peaks in it, and we would like to extract those features. A doctor who looks at ECG essentially searches for those peaks and also searches for anomalies in those peaks, and those anomalies could be an indication of an unhealthy heart, for example. So, feature extraction is very common, not just of course in biomedical, but everywhere. And classification. Once we extract features, we would like to classify image. In image analysis, this is a very common exercise. We try to classify people with similar colors, hair color, similar eye color and facial skin color and so on. And then central to all of this is hypothesis testing. What is hypothesis testing? It is a very common exercise in data analysis, where the researcher postulates the truth being something. As an example, suppose I collect ambient temperature data that is outside my room. I take a sensor and collect ambient temperature for about maybe an hour or so, and I come back and postulate that the average temperature during that 1 hour is 25 degrees Celsius. Now, that is a truth that I postulate for the average temperature, and hypothesis testing is about testing that claim that I am making, whether it holds or not based on the data that I collected. So, the data that I have collected serves as an evidence, and I search for evidence in the data to support my hypothesis, and that has to be done in a statistically sound manner, and hypothesis testing is an integral part of every statistical inferencing exercise. That involves, of course, a lot of theory, probability theory, estimation theory and so on. We will not go into depth in hypothesis testing and so on. There is a MOOC course that will run on introduction to hypothesis testing that will begin perhaps in the 2nd or 3rd week of March. And if you are interested, you should sit through it, because it is an integral part of every statistical data analysis exercise. Then we have data analysis being carried out probably for fault detection. As I explained earlier, when the doctor looks at the ECG, is looking for anomalies, or when a radiologist is looking at the X-ray, is looking for anomalies based on some model or some template of normal conditions in mind, keeps projecting the present data onto that normal template, and that is how typically fault detection is carried out everywhere, even in process industry. That is the situation. So, this is also known as process monitoring, and there are several purposes which that one can list in data analysis, but these primarily cover most of the applications of data analysis. As you can see, the applications are quite diverse and varied. Therefore, the procedure that we follow for analysis, the tools that we deploy and the interpretations that we draw have to definitely vary broadly. So, it is useful to look at data analysis and ask where does it fit in the broad scheme of data driven analysis. So, this pictorial representation here tries to give you some idea of where analysis fits in. At the top of the schematic, you have process, and this process is a very generic process. It need not be an engineering process, it could be a social process or a biological process and so on. And we have sensors collecting data from the process, and these sensors need not be just the classical hardware or instrumentation sensors, it could be also human sensors. When we collect survey data, we are the sensors in fact. In the end, we have data with us, and that is where the journey begins in data analysis. In this module, of course, we are not going to talk about how to collect data, the techniques of sampling and so on. We are more worried about analyzing data. So, once I have data, typically I put it through certain steps, and we will talk about this a bit later. The purpose of this schematic is to tell you where analysis fits in. The two stages that you see titled analysis here, it is essentially the representation of what goes on in data analysis. So, for example, visualization is a part of analysis. When you plot something and try to observe something from the data, that is also a part of the data analysis. It is a very important part. Or you may carry out parameter estimation, as I just discussed, or you may build models and so on. Ultimately, the results from this data analysis go into some of these very broad applications, as I just explained. It could be for process monitoring, that is fault detection, or it could be for process control, where I am taking feedback action based on measurements. So, the controller is taking in the data, performing some kind of analysis and then deciding how the input should move. That is also a part of the applications of data analysis or optimization. I am trying to come up with an optimized way of operating the process or making innovations or changes to the process. Then of course, there are a few other applications that I have not listed here, but ultimately you should understand that data analysis is not the end of the road, but it is really a very critical part of data driven process analysis, process operations and so on. And when I say process here, as I mentioned earlier, it is fairly generic. And in all of this, of course, the domain knowledge is very important, as I highlight here, and we will talk about this a bit later when we return to the schematic and discuss the systematic procedure that is involved in data analysis. So, hopefully you understand where data analysis fits in. It actually connects the world of observations to the world of information. Right. There are many different types of analysis, obviously, now depending on the need and the end use of your analysis. And there are several classifications that you can find in the literature, and what I have listed here is by no means exhaustive. One of the common classifications of analysis that you see is exploratory versus confirmatory. In an exploratory type of analysis, you do not postulate anything upfront, but you are just exploring the data and trying to understand your process. For example, it could be looking at the mean or the standard deviation or looking at the graphs, trying to understand whether the process is linear or stationary and so on, trying to infer whether the process is oscillatory and so on. So, a lot of visual plus some descriptive statistical analysis is involved. Whereas in confirmatory analysis, you have a postulate upfront and you would use the data to confirm whether what you have in mind is correct or not. So, obviously, there is a bit of contrast there. And then you have quantitative versus qualitative data analysis. In qualitative data analysis, for example, you look at trends, you are searching for certain features and oscillatory features, for example, whereas in quantitative you are looking at numerical results from your analysis. Then you have something called descriptive versus inferential, and in descriptive analysis again it is more or less like exploratory, whereas in inferential you are trying to infer something very specific from data and you are subjecting it to a hypothesis testing. So, there is a lot of systematic numerical and statistical analysis involved in inferential analysis, and this could be a part of a larger analysis that you are doing, such as building a model and so on. Whereas descriptive analysis is not necessarily going to feed directly into a larger analysis. It is typically the first step in data analysis. Then you have predictive versus prescriptive. Predictive analysis is about asking where the process is heading based on data, and this is very useful in many applications. Whereas prescriptive is about asking why something has happened. So, you have looked at the data either as a doctor or as an engineer or even as an econometrist, and you looked at market data and suddenly there has been a crash, and you are asking, well, why did this crash occur, or why did a particular fault occur in a process and so on. And then you are of course going to suggest as to how to prevent this. So, there is going to be a diagnosis and remedial thing involved in prescriptive analysis. Obviously, there is a whole host of different types of analysis that are involved, and there are many other classifications that I have not listed. Typically, good starting points are exploratory and descriptive analysis, and then one proceeds from there. Even if you are if you have decided that you are going to build a model for prediction and so on, it is recommended that you explore the data, you make friends with the data, you familiarize yourself with the data before you proceed to developing a model, for example. Now, in general, the objective of analysis determines the specific types of analysis that we have listed here that you would carry out. That means essentially what is the end use of your analysis, how are you going to use the information that you extract. And before we proceed to data analysis, it may be very useful to know what are the different types of data that are available, because primarily, as I will mention later, the tools, the interpretations and so many other steps depend on the nature of the data. Now, once again when you turn to data analysis literature, you will find different types of classification. A number of classifications exist. For example, you may find numerical versus categorical classification, or steady state versus dynamic, and so on. But I am not going to really talk about those, because that's definitely important, but what is more important, which people often ignore, at least beginners in data analysis often ignore, is this classification of deterministic versus random or stochastic data. Now, that is very, very important, because theoretically itself or the theory itself largely differs the moment you say the data has come out of a deterministic versus stochastic process. Now, of course, some people use the term random. There is a subtle difference between random and stochastic. However, we will not observe that distinction here. Sometimes the term non-deterministic is used. Before we ask why this classification or distinction is important, let us look at the definitions. And the definitions are based on the data generating process. So, the deterministic and stochastic qualifiers are not for the data per se, it is actually they are qualifiers for the process that is generating data. In data analysis, the data generating process is a very important entity. What we mean by data generating process is the process that you are collecting the data from, as well as your experimental process, that is how you have conducted the experiment and so on. So, put together everything is the data generating process. It is not just the physical process alone that you are analyzing. That is very important to remember, because both contribute to the type of data that you generate. As an example, let us say I am observing some reactor temperature, which is being controlled by coolant flow. This is very common in nuclear reactors and so on. Now, the reactor that I am observing is a physical process. There is a controller there trying to control the temperature and so on. Let us say it is doing a fantastic job of controlling the temperature. So, the temperature is held at its set point. But the sensor that I am using can be quite noisy. Ultimately, the data that comes to me is not directly from the process. Between the process, the physical process and the data, I have a sensor. And that sensor characteristics, the characteristics of that sensor actually goes into the data as well. If the sensor is very noisy, you are going to end up with a noisy data. If the sensor has a bias, your data will show a bias. Now, the data generating process consists of both the reactor and the sensor. The DGP, as we shall use as an abbreviation that you will find even in literature, is said to be deterministic if you can find a mathematical function that can accurately explain the data. That is, it can predict the data, it can fit in perfectly. Every data point lies on the curve of this mathematical function. That is one way of looking at it. Or you can say that you have exactly understood the data generating process. There is nothing that you cannot explain, or that you can say there is no uncertainty in the observed values. You may have many a times what happens is you may have very good knowledge of the physical process. For example, the reactor in the example that we discussed earlier. I may understand the dynamics, the kinetics, everything in the reactor, the thermodynamics and so on, but I may have poor knowledge of the sensor characteristics. Now, that makes it a very tricky situation. It puts in neither in the deterministic nor the stochastic thing, and we will talk about it, but essentially that is not deterministic anymore. The data is not coming out of a deterministic process, because a part of the DGP, which is a sensor, has not been understood properly. In general, this is the situation. Sensors are never perfectly understood. You can design a very, very nice sensor that has very less noise, but no sensor is perfect and no sensor is really perfectly understood. So, in reality, there is nothing like a deterministic process. It is an idealization that is very useful in data analysis and in developing the theory. Now, obviously, stochastic is the counterpart for the deterministic, which where we say that the DGP is not accurately predictable, or it is not known, or you can say there is uncertainty in the data and so on. And as I said, in practice no process is deterministic, since perfect knowledge is not known. Now, does it mean that every data generating process has to be treated as stochastic? Not really. There is a certain distinction still observed between deterministic and stochastic processes even in practice, even though no process is perfectly predictable. Typically, we say that a process is predominantly deterministic or predominantly stochastic, and we will talk about it very soon after this slide here. So, going back to the question that we raised earlier, why should I worry about whether the data has come from a deterministic or a stochastic process? Why is this assumption so important? Now, the answer is something that I have said earlier. The theory, the tools for analysis and the interpretations of the results significantly depend on these assumptions. And there are many examples that one can give. For example, if I am looking at periodicity detection, then first I have to define what is a periodic deterministic signal if I am looking at deterministic data, and if I am looking at stochastic data, then I have to define what is meant by periodic random process. Now, the definitions vary, right, and therefore, the interpretations will also change. Likewise, when I am referring to the average of a stochastic signal, normally a misconception is the sample mean, which is the mean that is computed from observations, is considered as the mean of the process itself. That is, it is not true at all. The sample mean is only an estimate of the true mean, which is defined in a different way, and we will quickly talk about it. So, the bottom line here is whether you are looking at mean, variance or any other characteristic of the signal, you have to really go back to the books and ask how are these defined for the signal that I am looking at. If I am looking at a deterministic signal, what is the definition of periodicity? What is the definition of mean? If I am looking at a stochastic signal, what is the definition? And then only you can make meaningful interpretations. And a very common situation is that of power spectral density, which is used for periodicity detection and so on. Anyway, we will not go so much in detail, but you should remember this fact, and every time you collect data and you sit to analyze the data, do ask certain important questions, and one of those questions is what assumptions am I making about the data generating process. So, before we move on to learning what is a procedure that is typically followed in data analysis, it is again good to close this discussion on deterministic or stochastic with this question, when do we assume the DGP to be deterministic or stochastic? Does someone come and tell me that? Obviously not. Can I find in the literature? Sometimes yes, but most of the times no, for the process that I am looking at. So, is there a way to know a priori? Well, unfortunately, there is no perfect formula for you to figure out whether the data is coming out of a deterministic or stochastic process, but you have to go by how much you know vis-a-vis how much you do not know, right. That is about the process. So, as an example, suppose I hold a ball in in a room where there is not much breeze, the air is fairly still, and I am going to drop the ball. We can pretty much, with the help of physics, calculate how long the ball takes to hit the floor. That is fairly deterministic process. There is not so much uncertainty there. On the other hand, if I were to be asked whether it is going to maybe rain tomorrow, or in 6 months it is going to rain, or if I look at any other atmospheric process characteristics, or even econometric process and so on, or a sensor noise and so on, it is very hard to predict what is the next value of the error in the sensor, for example. In such situations, we take asylum in probability theory and we say that, look, I do not have a perfect knowledge of the process, therefore, I shall assume that there are many possibilities and I assign chances to each of those possibilities, and that is where probability theory takes birth, and that is where time series analysis comes in. There is also another situation in which you may have to assume the process to be stochastic, and that situation is where the cause of the data that you are looking at is unknown. So, as a simple example, suppose I am looking at the prediction of stock market index. There are so many causes that actually affect, there are so many factors responsible for stock market index. Now, unfortunately, even if I know the causes, I may not be able to measure them, and sometimes I do not even know the factors exhaustively enough. So, what do? I depend on the history and hope that history has some repetition in it, and I exploit the historical patterns and correlations and so on, and make a prediction, but that prediction is going to be obviously not accurate. The point is here, we, apart from looking at a history, the main assumption that we make is that this stock market process, that which is some fictitious process that is generating the index, is random in nature. It can throw out any value of the stock market index out of which I am observing one. There could have been many other possibilities out of which one has occurred. In reality, that may not be the case. The true process may not be behaving that way. It is an assumption that I am making so as to move forward in data analysis. That is very, very important. In other words, whenever I assume a process to be stochastic, it is a formal way of saying I do not have sufficient understanding of the process. But there are situations where I have a mixed case, where I have a fairly good knowledge of a part of the process and the other part of the process is beyond me. That is where we have a mix of deterministic and stochastic process, and that is very common in engineering arena, because the physical process may be well understood, like in the reactor example that we discussed earlier, but the sensor or some effects of unmeasured disturbances, something that is beyond my control, those have to be treated as stochastic simply because I cannot predict them accurately. So, there we may have to deal with both the deterministic and stochastic components, and there is a theory that allows you to do that. So, the bottom line is, please do spend a few moments asking why, first of all, whether you want to treat the data as a deterministic coming out of a deterministic or stochastic process or a mixed process, and you should have the answer as to why you have made that assumption, because the course of analysis really depends on that. Okay. So, just to emphasize, be clear on why the data is assumed to be non-deterministic, particularly this is a very common assumption. In fact, many researchers carry out data analysis assuming the data to be stochastic without probably even pausing for a moment to ask why and what kind of stochastic. Just because I assume the data coming out of to be coming out of a stochastic process, I cannot simply go ahead and carry out my data analysis. Within the stochastic processes, there are several classifications, and I have to be clear in my assumption. It is after all an assumption, but still I have to be clear as to whether it is coming out of a stationary stochastic process, non-stationary stochastic process, or a periodic stochastic process, and so on. So, there are different categories, and we should be very clear. All of this is apart from the regular classifications that we have to think about, which is whether the data is coming out of a steady state or a dynamic process, linear or non-linear. All those still hold good, but this is a very important classification that you have to make upfront. And in general, if you have access to the experiment, this is of course outside the purview of data analysis, but it is related to it, suppress the sources of randomness if possible during your experiment. That is a topic that is dealt with in detail in design of experiments, and we do not go into that here. The most important thing that people often miss out on, at least beginners, is that any estimate or any inference that I draw from data, and typically lot of data is assumed to come out of a random or a stochastic process, those estimates or inferences are also random in nature, because you are putting through data which has uncertainty in it through some mechanism, some formula, some mathematical process, and you are getting out, for example, I am computing the sample mean. I go and collect data, ambient temperature data with a sensor, come back to my desk and feed in the data into my computer or my calculator, and I actually compute the sample mean. The sample mean that I have calculated is simply the average. Average of what? Data that is corrupted with uncertainties. So, those uncertainties have also made their way through to your sample mean. So, the value of sample mean that you have has also some uncertainty in it. The uncertainty here is not with respect to your calculation error, okay? That should be kept aside. The uncertainty in it has got to do with the fact that you are not sure if this is the true mean of the process. That is the uncertainty. That is again because the data that you have collected is one of the many possible data sets that you could have collected. So, you have a sample mean which is one of the many possible sample means that you could have obtained. And this is true for any parameter estimate, whether you are estimating slope, intercept or any other correlation, any other complicated parameter that you may be estimating from stochastic or statistic data, you will have to remember that there is an error in the data, and as an analyst it's the responsibility of the analyst to compute the size of the error or the uncertainty in the estimate or the inference that you are drawing. That is a very important part of data analysis. And in this context, you should choose an estimation method that gives you an estimate with as small error as possible, and we will talk about it a bit more in detail. More importantly, that as you collect more and more observations, the error in your estimate should ideally start shrinking and go to 0 asymptotically as n goes to infinity. So, these are some criteria, and very often many of the researchers may not be aware of this. So, before we move on to the data analysis procedure, which is the last part of this lecture, it is important to at least gain familiarity with some terminology that is commonly found in the data analysis literature. And here we will assume primarily that we are going to deal with data that comes from a non-deterministic process, because that is the prevalent situation everywhere. Even if you have a mix of deterministic and stochastic process, these terminologies apply. So, the first terminology that we have to be familiar with is the term population and sample. We know that in stochastic process, as we just mentioned earlier, we observe when we get a data record, the record of data that we have is one of the many possibilities, sometimes countably finite, sometimes countably infinite or infinite. Many possible data records exist out of which we have observed on. That is the theory. The entire theory is built on that premise. The population refers to all possibilities that you could have seen, although we do not observe that. It is not possible to really have or observe all the possibilities in most of the situations. So, population refers to the collection of all events or possibilities. With respect to the temperature measurement that we talked about earlier of the ambience, if I collect 100 observations with one sensor over a period of time, another sensor would have viewed that in a different manner. So, that another data record could have been possible, or the same sensor itself could have recorded everything held constant, could have recorded completely different values. So, it is not possible obviously to realize all those possible values, but theoretically it is important to imagine this all possible space, and we call it as population, of which we obtain one sample. When I say sample here, it is not one observation. A sample in statistics typically refers to a collection of observations. It basically refers to one data record. But in signal processing, a sample could mean one value at an instant, and that is in the deterministic world. Corresponding to this population and sample, we have a truth and an estimate. We just said population is a collection of all possibilities, but that is characterized by the truth. So, this entire population has, for example, certain mean. Let us say I am looking at the average salary of a group, of an age group in a very large country, let us say, or in a very large firm. It is not possible for me to go and ask everyone. I may, for practical reasons, I may only select a few people to ask, to collect this information about their salary, and from which I infer the true average salary. So, the true average salary is a truth, that is what characterizes the population, that age group, and estimate is what I obtain from data. Obviously, estimate will always be different from truth, because I have not seen all possibilities, and the estimation theory tells you how to estimate the parameter of interest in an efficient, consistent way from the data record. Associated with this, you have this estimation, you have these terms called statistic and estimator. A statistic is nothing but a mathematical function of your observations. Again, the sample mean is a statistic, sample variance is a statistic. It is simply a mathematical operation that you are performing on the observations. An estimator is also a mathematical function. It's you can say a soft device or a virtual device that operates on the data in a mathematical way and gets you the estimate, an estimate of what you want. The difference between statistic and estimator is fairly subtle. Prima facie they appear to be the same, but the difference is statistic is merely a mathematical function, not necessarily devised for any purpose, whereas an estimator is a mathematical operation that is carried out with a specific purpose of estimating something in mind. Okay. So, if you go down further in the estimation theory, you will see more discussion on this difference between statistic and estimator. But as far as the mathematical operation is concerned, both are mathematical functions of the data. So, in estimation theory, we use these statistics and estimators quite often. So, sample mean is both a statistic and an estimator of the true mean, all right, because sample mean is devised for estimating the true mean. And again associated, as you can see, it is all about the population and sample. You have ensemble and sample averages. Ensemble average is the average that you would compute from all possible values that you could have ever seen, which of course we never get to see in most of the situations. We never get to collect all the possible data records, or in the salary example it may not be possible to collect the data from all possible people in meaningful time. Sample average of course is simply the average computed from the samples, and these averages are used to define what is known as an ergodic process and so on. We will not go into that. Finally, the two terms bias and variability are very important in data analysis, because they both talk about the error that one makes in estimating some parameter or a set of parameters. Bias is a systematic error that one ends up making. Every estimation exercise or will give you an estimate that is in error, there is no doubt about it. The question is whether the difference between estimate and truth is by chance or due to some deficiency or shortcoming of your estimator. How do you know if there is a bias in your estimation exercise or in your estimate? Imagine this thought process. I have collected, let us say, 100 data records or 1000 data records for one process, and I compute the sample mean for each of the data record. If I average, let us say not even 1000, about a million data records, for per data record I have one sample mean, and for million data records therefore I have million sample means. If I average the sample means, that the million sample means that I have, I should be very, very, very close to the truth. If there are only million possibilities, I should get the truth. But if there is a difference that still exists between the average of this million sample averages or sample means and the truth, then there is a systematic error. This ensemble average that we talked about as I have written above is also known as expectation. So, in other words, if coming back to bias, if the expected value of the estimate is different from the truth, then we say that there is a bias in the estimate. Now, coming to variability, it is a measure of the spread of estimates across different data records. It is very, very important, because in practice I only work with one data record and I make all my inferences from a single data record. I need to know, had I the answer to the question, had I collected another data record and had I made the drawn the inferences from the data record, would those inferences be significantly different from what I have seen now? They will be different obviously numerically, but will the difference be too large? And if that is too large, then we say there is a large variability in the estimation or in the estimate. For this reason, variability is also referred to as precision. The lower the variability in the estimate, the more precise is the estimator. In contrast, bias measures accuracy. Lower the bias, lesser the inaccuracy. In fact, zero bias would mean it's an accurate, the estimator is an accurate, gives you an accurate estimate of the truth. Typically, we are more worried about variability. Yes, of course, we want an accurate estimate. Ideally, we want an accurate and a precise estimate. It is not possible to obtain both an accurate and precise estimate from finite samples. But what definitely we would like to have is low bias or zero bias if possible, and as small or low error as possible. That is why you see on many instruments that are being supplied to laboratories, you have these instruments being qualified as high precision instruments. Remember, estimation is not just about V using a mathematical formula on data. Even a sensor, actually the reading that it gives you is an estimate of the truth. So, one should have a very broad view. So, what the company or the manufacturer means by high precision instrument is, if you were to repeatedly measure the same variable with a sensor, you would not see too much variability. Definitely there will be some variability. So, take a thermometer and place it on your body and take the reading, note down the reading, then again take the thermometer and then place it on the same part of the body and take the reading. Of course, you will probably see the same reading there because thermometers do not report beyond first decimal, but you may see an actual variability if you have thermometers reporting maybe the 4th or 5th decimal and so on. That is called resolution of the instrument. But anyway, the point is, repeated measurement of the same variable definitely will give you different readings, but you do not want wide variations in those readings. So, you want a high precision instrument. So, with that we come to the close on terminology or the major terminology. Of course, there are many other terms that one would want to be familiar with, but those are the basics. We will conclude the lecture with the procedure that one needs to follow for data analysis and then move on to a couple of illustrative examples in R. The foremost thing to remember is that almost all data analysis procedures are iterative in nature. Do not expect step 1, step 2, step 3, step 4 done. It is never going to be that way, very rarely. So, they are not necessarily sequential, but there is a certain order in it. It does not mean that you go about doing in a haphazard manner. And also remember that the success of any data analysis exercise depends on two things: the quality of data that you collect and the systematic procedure or the methods that you tools that you have used in data analysis, or the entire methodology of data analysis that you have followed. If the data quality is bad, you cannot do much. Even if you follow a systematic procedure, you may not get marvelous results. And even if the quality of data is good, you follow a very unsystematic and you use a procedure and you use a very poor estimator, you may end up with a poor estimate. So, both are important. Now, of course, quality of data is many a times is not in our hands, but you should still be aware of the theory to be able to say, when you look at a data and say that, well, this data quality is not good, so I should not expect good results. So, suppose you are a consultant and you have been given some data, you are hired for data analysis by a process industry and you are given some data. The first thing that you should be doing is look at the quality of data and make an intuitive assessment of how good or the nature of the results that you can expect. If the data quality is too bad, you should return the data and say, well, do not expect miracles. The data has to be collected in a much better manner so that it is so called informative. Alright. So, please keep that in mind. Now, we revisit the schematic that we saw at the beginning of this lecture, which gives us some idea of what is a systematic procedure of the data analysis. So, at the top we have, of course, the data coming out of the process, well, out of the sensors, and the first step in data analysis is going through some preliminary steps which involves three things: visualization, quality check and pre-processing. Now, again within this it is not necessarily sequential. Generally the first step is to plot or the data, because numbers may not tell you much, but pictures tell you a lot more. And to emphasize that, let me actually take you to this slide here. This is a very classical example based on what is known as an Anscombe data set, and this data set is also available in R. R has many data sets that come with it when you install. Now, the beauty of this Anscombe data set is, let me explain what I show you here. I have 4 data sets here of pairs of variables. Think of x1, y1, x2, y2, x3, y3 and x4, y4. They all look visually very different. However, if you had not looked at the data and you had computed, for example, mean or variance, or you had fit a model between the respective pairs or computed a correlation, they will all be identical. They would all be identical. So, they based on the descriptive statistics you or even your regression, you would not be able to make any distinction between these 4 data sets. However, as you can see, there is such a wide difference in the features of each of this data. For example, if you look at the data set 2, there is a parabolic kind of relationship, whereas data set 4, all the points fall on a straight line. Practically, there is no change in x, only y is changing apart from one outlier. So, this data set is also very useful to show you what outliers can do to your data analysis. Outliers are those data points that fall out of the normal thing, or that fall out of the region where the rest of the data are. In fact, if you look at data set 3, all the data points lie on a straight line except for one data point, that is an outlier, right. So, 2 data sets can look completely identical when you look at descriptive statistics alone, whereas the moment you plot them, you know there is a huge difference, and then of course, you will take corrective action and the necessary steps to be able to extract the features correctly. So, that hopefully this drives home the need for visualizing data prior to any data analysis. And then of course, we just did a quality check. For example, we observed the presence of outliers, that is very important. Many a times data comes with missing values. You have to decide how to deal with missing values. There is a whole lot of theory available, whether you should replace it or live with it, interpolate and so on. So, obviously, it is not possible to talk about it here. And then other kinds of pre-processing that you may have to do. For example, you may have to sync the timestamps in multivariable processes where you collect data from of different variables. You may have to sync the timestamps, or sometimes one variable is collected at one sampling rate, another variable is collected at another sampling rate, then you may have to determine how to pre-process. Sometimes, in fact, lot of times the data comes with noise, and we may have to remove the noise prior to any other step that we may take in analysis, because noise really can hijack the inferences that we draw. It can significantly affect the course of data analysis. So, we may want to filter out and so on. So, there are many reasons why you want to spend time in this preliminary step, which is perhaps the most important. There is some bit of there is a bit of drudgery involved in it. It can really get onto your nerves, and there is a golden 80-20 rule which says, of the 100% of the time that it takes for overall data analysis, you may have to spend 80% of the time on data pre-processing. That is the kind of effort that you may have to put in sometimes. If you are lucky, of course, you can just go pass through this step in a breeze. Then comes, of course, the core part of your analysis, which is modeling or estimation or exploratory or maybe predictive kind of or prescriptive kind of analysis, diagnosis and so on, which the results of which feed into many applications such as monitoring, control, optimization, innovations, as we have discussed earlier. Now, very importantly, in all of these steps, you should keep in mind 2 things. One, as the arrows indicate, they are not necessarily iterative. That means sometimes you may have to go back. So, if I find that the data quality is poor, I may have to go back to my experiment or the person who gave me the data to give me better data, or that I find that the features that I want are not present in the data, I may have to redo the experiment. or after estimation I figure out that the data quality is not good enough, or that I have not done sufficient pre-processing, I may have to go back, and so on. That is the first point. And the second point is, if you have any domain knowledge, and that is very, very important. Obviously, you should know where the data is coming from, whether it is coming from a biological process, an econometric process, or an engineering process, or some social media process, or and so on, right, or a chemical process and so on. That knowledge should be factored in at every step, even in choosing what should be the sampling rate for your data. That is, how often you should collect the data. That is where your journey of domain knowledge begins. And if I know, for example, I am looking at a pH system, I know it is a nonlinear system, right. Then I should, when at the modeling stage, I should not even think of building linear models. But if I do not know where the data is coming from, it just remains a data set, and it is of limited use to me. It is just some kind of a toy that I am playing around with. So, the domain knowledge has to be used at every stage in the best possible way, and that completely depends, of course, on how much domain knowledge you have. It may help you in choosing the structure of the model, the kind of features that you should search for, or the level of noise that you can expect, whether it is sensor noise or process noise and so on, or even in your applications. So, that should be kept in mind. All in all, iterative in nature, but there is a certain systematism to it. Choose your models properly and make sure that you go through the data quality check, visualize the data, pre-process, then choose your models properly if you are building models and so on. We will talk about that in the next lecture on modeling skills, or estimate properly and so on. So, we will now expand on this a bit more. So, before we proceed to data analysis, the first step, as we learned, is to ask certain preliminary questions. What type of analysis is required, whether it is descriptive, predictive and so on, because that changes the entire course of analysis. Where does the data come from? Sources of data, as we have just asked, do we have time domain data, frequency domain data, biological process data and so on. How was the data acquired? What kind of hardware was used? Was it a human who collected the data? Was it a sensor? If it was a sensor, what was the sampling rate? So many questions may have to be known for us to be able to say how good a quality of analysis that I can expect, and what should be the kind of analysis tools that I should be using, and what should I be searching for. And then, of course, how informative is the data? That is a bit qualitative, but there are also certain quantitative measures of information. We will not talk about it, but as I said, it basically pertains to quality check, whether there are missing data, outliers and so on. And lastly, but perhaps the most important, what assumptions are being made on the data generating process. Should be clear. You may be wrong in the beginning. We may make wrong assumptions. We may assume a stochastic process to be deterministic. We may assume a nonlinear process to be linear, a steady state process to be dynamic, and so on. It is possible, but we should stick to the assumptions that we have made throughout the data analysis, and choose and be consistent and commensurate. That is, we should choose the right tools and so on, so that if we have made a mistake, in the end we do know that we have made a mistake, and then we go back and make corrections. And I am not going to really go into this detail, we have already talked about it. So, once we have through the preliminary questions, we prepare our data through many data pre-processing steps, depends on what kind of problems the data has. For example, if the data is outliers, I may have to clean up, but there are also robust methods which say let the outliers stay in the data, I am still going to get you decent estimates and so on, or we may have to filter and so on. The one thing that I did not mention earlier is partitioning the data. If you are building a model, or if you are performing classification by extracting features and so on, always you should have a part of the data in hand for cross validation. You should we should take the model that we have trained on the data and test it on a fresh data which has come out of similar experimental conditions. Or if we have built a classifier based on the training data, then we should test that classifier on the part of the data set that I have obtained. So, always keep a portion of the data set for cross validating. And sometimes it may be necessary to assess quantization or compression errors that may arise in data that come from historians. These days it may not be so bad, but if you are looking at data maybe 10 years ago and so on, they may have been highly quantized or compressed, and that can significantly change the course of your data analysis. They may introduce unnecessary nonlinearities which are not a part of the physical process, it is just a part of your data acquisition process. Then of course, we talked about visualization wherein we could look at simple trend to high dimensional plots, bar charts and so on. The list is obviously not exhaustive, but always convert numbers to pictorial representations before, during and after analysis. So, visualization is a integral part of every stage of the data analysis. We have talked about the Anscombe data sets that basically emphasize the need for visualization. The core steps in analysis is what we will talk about and then conclude the lecture. Select the domain of analysis. What we mean by domain here is whether we want to analyze the data in the same domain that it has been obtained. Normally the time is a domain, independent domain in which we collect data. But we may not want to analyze the data in the time domain. Sometimes we may want to move to frequency domain. In fact, that is a very common procedure that is followed in periodicity detection. If you look at atmospheric data or even many data coming from vibration machinery, ECG or EEG data, for all such data, the frequency domain analysis is a very convenient domain of analysis, because it reveals the features that can be directly related to physical characteristics of the process. And of course, many a times you may have to do a joint time frequency analysis, wavelets is one of them. So, select the domain of analysis, and time need not be done, it could be space also. Many a times data can come to you as a function of frequency straight away, like absorbance spectroscopy data comes as a function of frequency from the chromatograph. Then the second one that we may have to take a decision on is dimensionality reduction, and particularly when we are looking at large dimensional data. This is now increasingly becoming common. It is not possible to analyze multivariable data in large dimensions, particularly when it goes to hundreds and thousands and so on, and they are very common today. And machine learning algorithms come very handy in this respect. Principal component analysis, non-negative matrix factorization and many other dimensionality reduction techniques are very powerful in analyzing large dimensional data. And so, we may have to take a decision whether to analyze in the dimensions that in which I have obtained, or in a reduced order or a lower order dimension. And most importantly is to choose the right mathematical or statistical tool. For example, if I want to estimate the mean, I can choose sample mean or sample median as an estimator. Now, when should I choose a sample mean as an estimator? When should I choose sample median? There is no perfect answer for it, but there are some very good guidelines. If I know that the data is free of outliers and it is coming out of a Gaussian distributed process, sample mean gives you the most efficient estimate, meaning estimate the lowest possible error among all the estimators. But if I know that the data could be corrupted with outliers and I do not want my estimate to be affected by it, then sample mean is not robust. That means it is very sensitive to outliers, then I should use a sample median. This depends on prior knowledge that I have and the knowledge that I have acquired from my preliminary data analysis step. And these kind of decisions have to be made at every stage, and there may not be unique answer. Remember that in data analysis there is no unique answer necessarily at every stage of your analysis, and even towards the end. Even when you build a model, there may be many models that can explain the given data, and you may have to actually pick the model based on some criteria. And likewise, in hypothesis test, we may have to choose an appropriate statistic. In analysis of variance, we may have to first know what the sources of variability are. Please guess fairly well enough. Or in modeling, as I said, you may have to choose the right regressor set and model structure and so on. And always factor in prior and or domain knowledge. You may know a priori something,
not necessarily related to the physics or the process, but maybe from the sensor characteristics and so on. And or of course, you may know something about the domain or the physics of the or the chemistry or the biology of the process that you can easily factor in and save a lot of headaches. And finally, once you are done with all your analysis, this is the most important part. Assessing what results you have obtained and reporting them is a very important step. Always subject any parameter estimate to a hypothesis test, whether it is significant enough, whether you have just obtained a non-zero value by chance, whether truly should have obtained 0. So, you should subject a hypothesis test of that parameter being 0, that is a null hypothesis, and then carry on in a statistically sound manner. And secondly, report confidence regions and errors in estimates. In fact, computing confidence regions and errors are an integral part of your hypothesis test. And then if you are building models, then cross validate models. When I say models here, need not be regression models, it could be classifiers also. And if multiple models are identified, use a mix of criteria, as I just mentioned earlier. There may not be a unique answer, typically that is the case. My students always ask me, well, I have 2 or 3 models explaining the data, which one should I pick? Well, the first thing is to make sure that you followed a very systematic procedure to minimize the number of solutions that you have, and even despite the best of efforts, you may end up with multiple solutions, very common. Then you apply what are known as information theoretic measures such as Akaike information criteria or Bayesian information criteria, and also keep the end use of the model in mind. Maybe your model has to be implemented online, so a simple model is preferred to a complicated one with a bit of sacrifice on the accuracy of the prediction and so on. So, again there is no unique answer, but in the end the final result that you report should have 2 things: a statistical backing to it and a sound argument to why you have decided to report these results and why the results are the way they are. So therefore, you should remember that data analysis is not just science alone. Yes, a big part of it is science, but an important part of it is also an art. Data analysis, therefore, both a science and an art. And never report estimates without reporting confidence regions and errors. As much as possible, you should definitely do that. In, of course, some very complicated parameter estimation problems, it may be very difficult to obtain confidence regions, but you should try despite the best of your put in the best of your efforts to report the errors and the confidence intervals. These are some of the references. Of course, no way it is exhaustive. I have taken some of the examples and some material from these books. These are quite common books, of which you may find the first book on random data analysis very, very useful to you, because these have been written by people who have practiced for 30-40 years, seen different kinds of data, and they have examples, very good examples in their textbooks. And the remaining 3, at least the book by Johnson and Montgomery and Ranga, they are classical books in probability and statistics, applied probability and statistics, and the book by Oganaike gives you the fundamentals of probability and statistics for engineers. So, if you are an engineer, you may be really interested in looking at the book. Of course, there are hundreds of other books that you can refer to. So, hopefully, you enjoyed the lecture and you understood at least what is data analysis all about, what precautionary steps you have to take, and how careful you have to be in data analysis, what is a systematic procedure, and some terminology. We will quickly look at a couple of illustrative examples in R, and that will hopefully supplement this lecture. Thank you.